Okay, thank you very much. First of all, I would like to thank organizers for making this wonderful event happen. It's very happy to be in IPAM in person. This is based on joint work with Melchior present here and Florentin Münch from Leipzig as well. So this talk is again about Ricci curvature, lower bounds in the non-commutative setting, as we have already learned from Mari's talk that asking such questions in the non-commutative setting can be a nightmare. And this talk, we are going through a similar nightmare from kind of different but connected paths. Okay, so I will start with the continuous setting, then the discrete setting, and then eventually the non-commutative setting, which is more or less the history, at least for the dynamical approach. So again, we will see this Berkeley-Emery stuff that characterize the Ricci curvature lower bounds. Say that, so actually we know that the Ricci curvature is bounded from below by K if and only if this gamma 2 conditions holds for the heat semigroup generated by the Laplace-Beltrami operator, where this gamma operator we have already seen in Mari's talk. And similarly, you can define a gamma 2, which will be recorded in the next slides. So namely, this suggests you that you can define the Ricci curvature lower bounds without a Riemannian structure. You just start with a good semigroup, and you define this Gachet-Duchamp gamma 2 operator, or equivalently, you state it in terms of this gradient estimate, then that should give you something like Ricci curvature lower bounds. Maybe this is a good point to do a bit calculation for this gamma operator in case you see this for the first time in Mari's talk. So let me start actually in the non-commutative setting. You have a semigroup, say it's just a unit and 2 positive. Okay, if you don't like, you just consider the classical semigroup where this matrix A is just the classical function. And we know this inequality holds because Cartesian-Schwarz inequality, or in the classical setting, just a Cauchy-Schwarz inequality. But this is not a good estimate in some cases. In some cases, because currently we are not using this semigroup structure. So sometimes you can improve this estimate as follows. You find a function that interplays these two quantities using the semigroup. Say you consider this is to be phi of t minus phi of 0. With this phi function defined as follows, it will be ps, pt minus s, pt minus s again. Then you know this is equal to, by fundamental theorem calculus, integration of phi prime from 0 to t, and when you compute this derivative along these semigroups, then you naturally get this Gachet-Duchamp operator. This integration, well, this is always non-negative, so certainly you get this estimate, but whenever you have a good control of this quantity, very often this gradient estimate present here, then you should have more information. So this is kind of basic idea. The other approach that we are kind of familiar with uses optimal transport in this program. It says that this Ricci curvature is bounded from below by K if and only if the entropy or relative entropy functional is K convex along the L2 Watson constant speed geodesics. So this allows you to define the Ricci curvature lower bounds whenever you have a good metric measure space, because you only need a metric to define the Watson distance and a measure to define the entropy or the relative entropy functional. So these are so-called Berkeley-Emery approach and the Lotus-Stone-Villani approach. A bit more about the basics about this gamma calculus. Say that you have a nice semigroup. I will not explain what it means by saying that it's nice. More information on this semigroup will come later in the discrete setting or the non-commutative setting. For now, you can think about this to be the Haonan-Zhang semigroup. Then we have already seen this definition of Gachet-Duchamp operator. You have two functions, nice function f and g, then gamma of f and g is again function. And it defines in this way because when you take the derivative along the semigroup, this operator gamma naturally appears. So in some sense, you can think about this as a first-order thing, first-order derivative thing along the semigroup. And if you take the second-order derivative, you will get something similar, which is this gamma 2 operator. It is defined in a similar flavor. And one nice property of the semigroup in the continuous setting is the diffusion property that can be understood as some kind of the chain rule identity. For this, maybe you can think about the heat semigroups that has Laplacian as a generator. Then this is nothing but the chain rule for the Laplacian. What it tells you that if you know the action of your generator L and this Garry-Duchamp over this function f, you should be able to compute the action of your generator over f squared, f to any power p, or logarithmic f, where here the psi some nice function, you have a composition here. Okay. And as we said, you can consider the Austin-Uhlenbeck semigroup. Then you can do a bit calculation. Then this Garry-Duchamp is nothing but the inner product of gamma f and gamma g, the gradient of f and gradient of g. And the gamma 2 here is the sum of the gamma part together with the Heisen part, which sometimes you can control by the dimension. But here we will not discuss the general curvature dimension condition here. So naively, you have that gamma 2 is bigger than or equal to gamma. So namely, you have the Ricci curvature lower bound with constant 1 for this OU semigroup. That is actually sharp. Okay, then a bit notation about the Wasserstein distance that we are already very familiar with. The only message here is that instead of a statistic definition, in the following we will consider the dynamical formulation given by the Bonomo-Brunel formula in the discrete setting or the non-commutative setting later. The connection to the Ricci curvature is based on a GKO theorem, saying that the heat flow is a gradient flow of the entropy with respect to the L to Wasserstein distance. If you further ask the convexity property of the entropy along the heat flow, then the Ricci curvature lower bounds naturally appears. So that's all that we want to recall in the continuous setting. Because of these two characterizations of Ricci curvature lower bounds, you can ask what happens to more general spaces, say the discrete setting. But somehow these two proposals do not carry over nicely because of some difficulties. Let me start with the basic setup. Say you have a finite set, and you have this irreducible Markov kernel with pi being the unique invariant probability measure. Then we will be assuming the detailed balance condition that is defined as follows. But in order to define such a detailed balance condition in a non-commutative setting, we don't have points, so we will start with the equivalent functional formulation. For that, let me introduce the inner products given by this invariant probability measure pi. First, on the class of functions that is defined over the space X. Then for functions that are defined on X cross X, and here the inner product is given by this k of xy, pi of x, divided by 2. Here you certainly have the symmetry here because you have the detailed balance condition. So with this, the detailed balance condition here is equivalent to the self-adjointness of the Laplacian with respect to the inner product that we just introduced here. And here the Laplacian operator is essentially given by the kernel subtracted by identity. Or you can alternately write this Laplacian as some kind of the square of the gradient. In the following sense, it is actually the composition of this discrete analog of the gradient, discrete analog of this divergence, so that we have the integration by parts formula with respect to the inner products that we just introduced. So in other words, here this discrete divergence is the negative of the adjoint of the discrete gradient with respect to these inner products. Okay? Any questions?
So these extra coordinates somehow represent your tangent space in a way. right?
X cross X, right?
Yeah.
Yes.
Tangent or totangent, that's hard to tell, but something like it.
Yes. Well, in this case, it's the same in some sense. So here is a brief comparison of the two proposals that we just mentioned in the continuous setting. When you try to adapt in this discrete setting, here for the Berkeley-Emery is kind of easy to define. You have the generators of the semigroup. By the way, semigroup will be the one generated by the Laplacian. Then you can define the Gaussian-Duchamp, which is not difficult. The same for the gamma 2 condition. Then you can say that, okay, we have Berkeley-Emery Ricci curvature lower bound whenever we have this gamma 2 condition. That is easy to define and sometimes easy to compute. This is a good thing. The bad part is that this is not so useful because on the discrete spaces, your chain rule identity is not so smooth. So you can hardly deal with some, say, modified log uplift inequality, and you don't have the gradient flow structure. For this reason, people introduce follow this Lotus-Stone-Villani approach or the entropic Ricci curvature lower bound. There you introduce the Wasserstein L2 Wasserstein distance in this discrete setting. Here we are using this Bonomo-Bohinier formula. The reason is that if you choose the statistical definition, even for just a two-point space, there is no non-trivial geodesics. Without geodesics, it's a bit hard to talk about the geodesic convexity, so defining Ricci curvature is a bit technical. So that's why people use this dynamical formulation, but one difference should be highlighted here, which was already discussed in some of previous talks. Say that you have a probability density rho, and somehow you want to define the multiplication of this rho to a function in two variables. You have two n's, x and y. You want to multiply by rho, so you can choose to multiply to rho to x, or you multiply to rho to y, rho of y. And somehow here we are choosing this multiplication given by this logarithmic mean for the reason that you have some discrete analog of the chain rule identity for the logarithmic function or the integration by parts irrelevant to some Fisher information type thing. But anyway, we are going to choose this rho hat to be defined in this way. And this way you have a discrete analog of GKO theorem, where the heat stem group, the semigroup, will be the one given by this Laplacian. You have the entropy or relative entropy, which is defined with respect to this invariant probability measure. And your Wasserstein distance will be the one that is defined in terms of this discrete Bonomo-Bohinier formula. So with this, you can define the Ricci curvature lower bound by asking the convexity of the relative entropy along the W2 geodesics in this sense. It has good things is such that whenever you have a good Ricci curvature lower bound in this case, you have, for example, modified log uplift inequality and many other things related to gradient flow structure. But the bad part is that in general, this is very difficult to compute. So the basic idea is that of this talk is whether you can borrow the idea from here, or in other words, whether you can combine the good parts of these two proposals. Here, it is easy to compute. Here, you have some interesting consequences. Can you somehow combine them at a small cost? So it will be helpful to give a unifying form of these two Ricci curvature lower bounds. It is convenient to use the gradient estimate. Here, for this Berkeley-Emery, you have this gradient estimate where this multiplication by rho is in some sense linear. You can multiply rho to the x or rho to the y if you want to take the arithmetic mean. Well, for these entropic Ricci curvature lower bounds, you can also define it in terms of gradient estimate, where this time it is very much nonlinear in rho. You need to use this kind of multiplication. But actually, what happens in most existing literature that we know in the discrete setting, to compute Ricci curvature lower bounds, you are not even using this kind of compact form. You are kind of using a gamma 2 type of formulation in this case, which means you further take the derivative on both sides with respect to t. Then this form is much more complicated. So that is why it is kind of hard in this picture. Okay? Any questions? Then we move to, okay, before we move to the non-commutative setting, let's see a few examples. Say you consider simple random walk on the cyclic group of order n, or the discrete torus, then which says that you jump to your neighbors with equal probability 1/2. Then in this model, we know that you have a non-negative Ricci curvature lower bound. It is sometimes maybe not so useful, but still computing this 0 as a Ricci curvature lower bound is not so easy according to the known result. Okay, you need to do some computation, and this is what you get. And for the next example, you consider simple random walk on the two-point space, or in general the discrete hypercubes of dimension n. This is to say that you have each point is represented as a string of m0 or 1s, and your neighbors are the strings that have exactly one different coordinate. So you flip the gist point, then you jump to your neighbors. And here we assume that the jumping rate is equally 1/n. In this case, one can prove a positive Ricci curvature lower bounds, which in this setup is 2/n. Okay, but
for functions or matrices of functions?
Here they are just the result in the discrete setting, which are just functions, nothing non-commutative yet, which will come now if we don't have any questions. And in the non-commutative setting, I will fix to the matrix algebras in this talk, and you will have a quantum Markov semigroup. The generator, I will consider the one that is positive, which is the same as in the Marius talk. And in this case, here is one example, by the way. In this case, let's have the following example in mind. It is kind of a very simple example, but talking about Ricci curvature lower bound, as we will see later, is already kind of not so easy if you want to achieve the optimal lower bound. So this is so-called dephasing semigroup. Say that you have an n by n matrix algebra. You have quantum state or the density matrices, for which I mean a positive definite with normalized trace 1, called sigma, and you have a continuous expectation E, whose adjoint with respect to the Hilbert-Smith inner product leaves the sigma invariant. Then the dephasing semigroup is defined as follows. Its generator is given by identity minus conditional expectation, or PD itself is a convex combination of identity and a conditional expectation in this way. And when sigma is equal to identity, this is nothing but the depolarizing semigroup. Okay. One kind of different thing, or one kind of different thing in the non-commutative setting is that you have a lot of symmetries because of non-commutativity. So recall that the detailed balance condition in the discrete setting is equivalent to the self-adjointness of your generator or the semigroup with respect to inner product of with respect to this pi here. The pi is the invariant state. Now say that sigma is an invariant state in the quantum setting, then that it may induce a lot of different inner products. The first one being the GNS inner product, we say that the quantum Markov semigroup is GNS symmetric if the following condition holds. It says that the semigroup or the generator is self-adjoint with respect to the GNS inner product that is defined in this way. Here you put all the sigma to the left or to the right. Well, to compare, we sometimes also need to consider the KMS inner product, where the sigma is divided into two parts equally, and multiply sigma to the 1/2 on the left and sigma to the 1/2 to the right. Another type of symmetry is given by this BKM inner product, and this time you multiply sigma to the s to the left, sigma to the 1 minus to the right, and you take the average. Okay. Currently, we know well about the GNS symmetry case. In this case, we can construct a non-commutative analog of Watson-Stan distance for which you still have the gradient flow, and you can define the Ricci curvature lower bounds. And for KMS symmetric, you need to know well about the generator that satisfies this inner product KMS symmetry. For in this case, we know something, but not fully understood yet. I mentioned this BKM symmetry here because Eric and Yan proved that the semigroup is a gradient flow, gives the gradient flow of some of the entropy with respect to some remaining metric, if and only if the semigroup is symmetric with respect to the BKM inner product. So this might be the right setup to ask in the full generality, and such a metric was constructed by Yan Mas and Maurice Brooks, but that metric is kind of hard to work with. Okay, so in this talk we will stick to the GNS symmetry, and we have seen this result of Alikey in some of the talks, which gives you kind of first-order differential calculus that is based on this very concrete form of your generator. Namely, a linear operator over this n-by-n matrix algebra gives a quantum Markov semigroup that is symmetric with respect to the GNS inner product if you can find the collection of this VG operator that is self-adjoint as a set, such that each VG is actually the eigenvector of the modular operator with respect to the eigenvalue e to the negative omega j. And then eventually your generator will look like this. Okay? And from here, Eric and Yan try to write this generator as a square of the gradient in some sense. Here in the following, I will keep notation clean, so I will just assume that the invariant state sigma is just trivial, it is just the identity, so you actually have the trivial symmetry. Then in this case, you can just write the generator as this partial adjoint partial, where this adjoint with respect to the Hilbert-Smith inner product, or in other words, it's just the sum of square of these partial J operators given by commutators of this Vj. Okay? Then in this case, you can also talk about Ricci curvature in at least in two sense. Following Bakri-Emery, it is kind of, again, easy. You can just define the Gary-Duchamp and the gamma-2 operators in a similar way. Then you can say that, okay, satisfy Bakri-Emery Ricci curvature, lower bound if and only if this gamma-2 condition holds. And the story is kind of similar. It has some consequences, maybe the spectral gap inequality, but if you want to talk about the exponential decay of the relative entropy or the modified locus Sobolev inequality, this is not going to be not very helpful, but it is easy to compute. So there is this approach of introducing a dynamical formulation of Wasserstein distance following Carl and Mas, that you define the Wasserstein distance in this way, then you still have a quantum analog of GKO theorem. This time, the semigroup is given by the one that we considered here, this semigroup that is GNS symmetric, that is a heat flow. The entropy or the relative entropy in general is defined as follows. So trace of rho log rho minus trace rho log sigma. Well, the Wasserstein distance is the one that is defined following von der Moe and Bohinian. So in this case, you have a gradient flow structure, and you can define the Ricci curvature lower bounds in a similar way. And the story is again similar. You have some good consequences of this. Say, you can use this to prove the exponential decay of the relative entropy, but it is in general very difficult to compute. And what people really tried at the very beginning is to start with the gamma-2 type of formulation of this gradient estimate formality here. So it's kind of a similar story in the discrete setting. And you try to prove a gamma-2 type thing in this case, which is kind of a horrible formula. You just differentiated this inequality with respect to t, and that is very hard to track. And again, in defining this Wasserstein distance, we need to discuss a multiplication in a similar way. Say you have a density matrix rho here, and you need to multiply actually to a vector field, but here just discuss the multiplication to a matrix A, and you are not taking the multiplication from left or from right. You are taking this multiplication with respect to the logarithmic mean. And this again, so that to ensure that you have some quantum analog of chain rule identity for the logarithmic functions in some sense. So now the picture is kind of similar to the discrete setting. You want to prove something, especially for this entropic Ricci curvature, which I will denote it by Ricci bounded by K for short in the following. And the goal of this talk is that we try to combine these two approaches in the sense that we try to derive this entropic Ricci curvature lower bound, which is in general difficult, from some gamma 2 type calculations from in the spirit of left-hand side. Okay? Any questions?
What's the curvature for Lx plus Ly?
By Lx, Ly, you mean the one that you just from the very beginning?
Yeah, Lx plus Ly.
We don't have that for general x and y.
So in M2, 2 by 2 matrices.
Yeah, 2 by 2 matrices. If you mean the Diploian semigroup, it will come later in the example. In general, it is 1/2 plus 1 over n equals to 2. It will be constant 1, which is sharp. That will come later. Okay. So it is, in general, a not easy thing to compute this entropic Ricci curvature. And Yan and Eric use a very simple identity, the intertwining condition, to study such problem. And this condition can be understood in the following way. Okay, this very simple identity, by the way, if you differentiate this identity, it will be some commutator of the partial and or the gradient and the generator. It is some multiple of the gradient operator. This is closely related to some formula in Marius' talk. So for this intertwining identity, you can just think about the following two very simple examples. If you have the heat semigroup, and actually the gradient operator and the semigroup commute in some sense, so partial j pt is the same as pt partial j, then this means k is equal to 0. And actually the Ricci curvature is indeed has non-negative Ricci curvature, and 0 is best possible. A very nice example is the OU semigroup, for which you can verify you have this identity with k is being 1. This can be seen from the Melchior formula that was highlighted in Eric's talk. So maybe let me remind you. For the classical OU semigroup, the Melchior formula says that the semigroup is a composition of 3 operators. You first construct the ID copy of your Gaussian, and you kind of embed your function in 1 variable to a function in 2 variables. And you do the rotation on this RD, not just RD, R2D. You do the rotation on the R2D, then you take a conditional expectation. Okay, from this you can verify directly that partial j pt of f will be, you will have this e to the negative t out, then pt partial j. That is easy to verify. So from here you can see that the curvature is bounded from below by 1, which is actually sharp. I will explain why this works later, but this is kind of a result of ideas. Then Eric and Yan discuss this bosonic OU semigroup, where they answer open question on the optimal convergence rate of the relative entropy towards the equilibrium. Namely, they notice that the similar identity intertwining condition is satisfied here for this semigroup, and from which you can derive Ricci curvature lower bound, then the modified log-Sobolev inequality, and this is actually sharp. But what about the other examples? Okay, certainly fermion case, something similar holds, and people then look for some example, something like a Gaussian, such as the Q Gaussian algebras where you have a similar O semigroup and actually satisfy similar identity from which you can derive some sharp inequalities of log Sobolev type. So you see here that I kind of skipped the discrete setting. I just jump from the continuous setting to a non-continuous setting directly, because it seems that such ideas were not applied to the discrete setting, because very often people try to find some Gaussian-like semigroups. And the goal of this talk is to kind of relax this condition so that you can apply this intertwining idea even for some discrete examples. Say the simple random walk on the cyclic group or the simple random walks on the discrete hypercube. Okay, now let's see why this simple intertwining condition could help. Say that we want to prove the entropic Ricci curvature lower bound in the non-commutative setting. Let's consider the case when sigma is equal to identity. So we're discussing the trivial symmetry. But already this gradient estimate form is not easy to prove. In the following, I will just reformulate this interval inequality as follows. It will be inner product of some operator acting on some vector. Take the inner product with the same vector, and you have something similar on the right-hand side. Here I'm using this lambda to be this multiplication by row operation, which is given by this logarithmic mean. Okay. Then let's assume that there's some kind of intertwining holds, and let's see why it helps. With this condition, so partial pt is equal to pt vector partial, then the vector on the left-hand side will be the same as partial A, that is kind of same as the right-hand side, and you have an additional semigroup to pt vector here. But that is what we are looking for, because now you can just consider the stronger estimate, namely the operator inequality behind it. Or in other words, instead of this estimate, you look for the inequality that holds for all elements, not just those that are living on the range of partial. So it seems that we are trying to ask something much stronger, but what is it good for? The good thing is that you can transfer this problem to an operator inequality, which you can linearize using the nice property of this lambda here. Okay? So this is a kind of idea you use in intertwining to transfer this problem to something that is harder, but you can linearize it. Okay, Eric has some nice perspective using duality and monotonicity of trace function that goes back to the Leibniz concavity theorem. But eventually, this problem is reduced to the following linearizing inequality, which, if you want to write down in full detail, it is something like this one. So in many examples that we can prove, eventually it is reduced to a Cartesian-Schwarz inequality. But as we discussed from the very beginning, Cartesian-Schwarz is kind of too rough. You can actually gain more information if you differentiate it. Then you get more information about curvature. So that was the idea in our previous work, and the kind of the new idea is from here you differentiate this operator inequality. So what we have discussed so far is that we start with an intertwining condition for the semigroup. Namely, we find pt vector such that this algebraic identity holds, and this pt vector is in some sense semi-flexible. On one hand, it is fixed over the range of partial because there is no choice. But on the orthogonal complement of the range of partial, you can actually choose pt vector to be anything. And the goal is to choose the pt vector over this orthogonal complement of a range of partial, so that this star inequality holds. Okay. And as we explained, if you just discuss this inequality, you will lose something. So maybe differentiate it. So in other words, in the following, we are going to consider problem at the level of generators. Okay, we need to find the pt vector such that this intertwining holds. Okay, it is the same identity for the generators. If you assume pt vector is also a semigroup, that is again semi-flexible. And now, if you differentiate the starting inequality, you will get something like a gamma 2 condition. it will be something like a gamma 2 condition. And this gamma 2 condition is somehow is something that you can really compute in the sense that from now on, our goal is to choose a good L vector such that these algebraic identity holds so that I can optimize my choice. I can choose my L vector. Okay, I know again that L vector over the range of partial, I can do nothing, but over this orthogonal complement of range of partial, I can choose whatever I want. And our choice is to choose this to be the multiple of identity over this flexible range. And then we optimize our choice of this multiple lambda. So this is the basic idea of the intertwining. And the idea that we transfer this problem of entropic Ricci curvature, we reduce this entropic Ricci curvature lower bounds to a computation of the quadratic things or Bakry-Emery type calculations at a cost of finding an L dagger satisfying this intertwining identity. Okay, I will explain with some examples. The examples even include some discrete examples. So this is kind of the study in this non-computer setting that provides some new perspectives in the discrete world. Say that you consider a complete graph example, then this is your Laplacian. And then following our previous idea, what we will do to prove the entropic Ricci curvature lower bound is as follows. You take any psi, and you write it uniquely as the sum of partial f, for which you can do nothing, plus this eta that is orthogonal to the range of partial with respect to the inner product that we introduced on x cross x. And our definition of L dagger over this flexible region is 2k times eta, where this k here is nothing but the real Bakry-Emery curvature lower bounds. So the choice of the k is really, you find it when you do this computation. And you can certainly compute this k that is at least 1/2 plus 1 over n. So in summary, what we did is the following. In order to prove an entropic Ricci curvature lower bound for this example, it suffices to choose this L dagger in this way, and you do some computation. The computation is essentially some gamma 2 type thing, which is something like this. Okay? And eventually you can show that the Ricci curvature is bounded from below by at least 1/2 plus 1 over n, which recovers some known results that usually relies on some heavy computation. Okay? Any questions?
Did you succeed in any calculation where the graph is not complete?
Yes. You can consider any graphs, then the lower bound can be negative. Well, it has to be negative. Lower bound is kind of negative 3 over 2 plus 1 over the minimum of your jumping rate. That is positive. But in general, this is negative.
So it's geometrically interesting, but doesn't give me inequalities, right?
Yes, you may combine some other conditions to derive things like modified log salvation inequality.
Is there any non-complete graph that you can have positive curves?
Like the Hamming cube example.
I mean, standard graph should probably have that.
Oh, that we haven't considered yet. Okay. So this is one discrete example, and this is one non-commutative example. The previous dephasing semigroup, this time the choice of L dagger is kind of similar. For any psi here, you write it as uniquely as partial of A, and the eta that is orthogonal with respect to the range of a partial. And the choice of L dagger here is almost identical. Over this flexible range, you choose to be 2k times identity, where 2k here is again, 2k here is again the real Bakry-Emery curvature lower bound, which you can show is at least 1/2 plus C of E over 1 plus C of E, where the C of E here is a Pearson-Popper index, which you can compute, for example, for the trivial condition expectation. That will be the deprived semigroup in the next slide. So the conclusion is as follows. In order to compute the entropic Ricci curvature lower bounds, what you can do is to choose this L dagger in this way, and you do some gamma 2 type calculation. You conclude that the entropic Ricci curvature is bounded from below by this Berkeley-Emery curvature. In particular, you have this lower bound. So when it comes to the depriving example, the C of E is just 1 over n or something, and this gives you the intertwining, this intertwining idea plus some gamma 2 type calculation tells you the entropic Ricci curvature is at least 1/2 plus 1 over n plus 1. Okay, you may, and this improves slightly the previous result that was known to experts. Okay, maybe this was written down or not written down in some existing literature, but previous results are something like 1/2 or 1/2 plus 1 over 2n. You may ask why we care about such tiny improvement. Just think about the 2x2 examples that Maris at the very beginning. The simplest algebra, 2x2 matrix algebra, the simplest the semigroup, the depriving semigroup. What is the entropic Ricci curvature lower bounds? Previously, you know it is 1/2 plus 1/2, with which 1/2 plus 1 over 6. Here we show that is 1/2 plus 1 over 3, but the best that you should look for is 1. Okay. This is what we can do, the best that we can do, at least in the current framework using this intertwining thing. But if you do a bit more computations, you can slightly improve to 1 over 2 plus 1 over n. Still tiny improvement, but at least for n is equal to 2, 2x2 matrix algebras, you know it is 1, which is sharp. Okay? Any questions? Okay, so
One more, but that goes back to your index. Sorry, I didn't catch that immediately. So if the index goes to infinity, you get 3 over 2? But then I could put this into a larger algebra, which has a bigger index, and go bound. I mean, isn't that a little bit surprising that if the index goes to infinity, your Ricci curvature won't get better? I mean, 1 is the best you can.
No, I think we messed
the
up
index
the
is definition
index
here is C.
the inverse of
So
the
that
Oh,
corresponds
it's the inverse of the
to 0 case.
Okay.
I wanted to correct that.
Yeah, sorry,
equal
my
to 0.
index goes the other way around. Okay.
Right.
So in infinite dimension, you will not gain anything. That's consistent with. If not, you
This
could go
is
to
known
large.
to be optimal
Yeah,
at 1/2
good.
infinite dimensions.
Okay. So Mario's question is actually about 1 over C of E, but it's kind of a maybe
Yes,
slightly
if this
different
goes to infinity,
notation.
the best thing is 1/2, and that's the best ever, right?
Yes, right. Okay, I think I may still have 5 minutes or so, and the rest is kind of the general framework that some people might be interested. I'm always discussing matrix algebra case and very often the trivial case. And I just want to, if you want to ask the question for the non-trivial case in the infinite dimensional setting, here is a dictionary to translate, okay? So first thing, you have this first order differential calculus for the genus symmetric quantum Markov semigroup with the help of work of Melchior. That is to say that in the previous Aliki theorem, where you have the different first order differential calculus given by this, that falls into this general framework of this data partial PT, VT, J, and this F thing, okay? And with this, you can define the gradient estimate. Here, maybe you maybe want to start with Watson's and distance, but in this case, a bit technical to define it and to verify that you still have the gradient flow structure. But if you want to, say, prove some function inequality like modify log subgraph inequality, suffices to consider this gradient estimate, which for the matrix algebras case looks like this. This was already studied in the paper of Eric and Yan. And if you want to discuss something more general, you can use this definition, where tau is a normalized state. F here is a function that witnesses this operator mean, and you use the data V operator and things in the last slides. So from here, you can define the gradient estimate for any operator mean. In particular, if you choose this operator mean to be this logarithmic mean, then this is, in some sense, the entropic Ricci curvature lower bound definition. And finally, what we have discussed so far that use this Bagrier-Emery type calculation to derive entropic Ricci curvature lower bounds also works in this setup with the cost of finding this intertwining condition. Namely, we want to find L dagger such that this condition satisfy together with this Bagrier-Emery type calculation, quadratic things. And eventually, this allows you to prove the corresponding entropic Ricci curvature lower bounds in this sense. And finally, we give a name, intertwining curvature bounded by Ks. This idea, again, is try to combine the good parts of the Bagrier-Emery proposal and the Lotustum-Villani proposal. One is easier to compute, the other one has some useful applications, but with the cost of finding this L dagger. Okay? Okay, I think I will just stop here, and thank you very much for listening.